Now, instead of two categories of colors, we have eight, right? How would a clustering algorithm likely interpret this? I would look at each candy and make the following conclusions. Each candy is in its own color. So, as an algorithm, without special training, it doesn't know the relationship between colors. For example, unlike human eyes, I do not know that the pink is closer to red than turquoise. So given this set of features, I conclude that there are 8 clusters and they are all equally similar to each other. I also conclude that out of 8 clusters, 4 are spicy and 4 are sweet. So because of this, mislead many kind of misinterpretation leads to serious problems like loss of grouping ability, inability to generalize, and wrong predictions. The model cannot form meaningful clusters because all features seem equally distinct, and inability to generalize. A new candy of an unseen color will confuse the model. It won't know where to place it. So wrong predictions may happen. Since all the clusters are equally similar, the algorithm might randomly assign spicy or sweet. Thus, even though we added more data or more colors, our model's performance decreased the exact opposite of what we expected. This is a perfect example of how the curse of dimensionality manifests in real world problems. So, dimensionality reduction to the rescue. To fix this, we apply dimensionality reduction, a mathematical technique that captures the essence of the data using fewer features. So, in our candy example, we realize that all colors can be represented using just two hidden variables, red exposure, blue exposure. So every color, whether it's a maroon, pink, turquoise or ocean, can be expressed as a mix of red and blue intensities. By converting the data into these latent features, we reduce 8 color features into 2. So simplify the data set. Restore relationships between similar colors like pink is equal to red, and at the same time turquoise is equal to blue, and it can be considered it is equal to blue. Ocean, it is considered to be equal to blue. Likewise, it can be considered. Now the model understands that candies closure in red blue exposure have similar properties, effectively rebuilding meaning from complexity. So this can be applied for the simplifier. Here, what is the new model does? It records each candy's color, transforms that color into two numerical values, red exposure and blue exposure, plots candies in a two-dimensional space where the x-axis is red and the y-axis is blue, calculates equilibrium distance between candies to find the nearest cluster. So these things has to be done. So assigns labels. Candies near the red cluster can be labeled as spicy. Candies near the blue cluster can be named as sweet. This process makes the model interpretable, efficient and generalizable, exactly what we want in machine learning. So, the dimensionality reduction, a mathematical technique that captures the essence of data using fewer features. In our candy example, we realized that all colors can be represented using just two hidden variables, red exposure, blue exposure. Every color, whether it is a maroon, pink, turquoise or ocean, can be expressed as a mix of red and blue intensities. By converting the data into these latent features, we reduce 8 color into 2 colors. Simplify the data set restore relationship between similar colors, like pink is equal to red, ocean is equal to turquoise or blue. So likewise, when we when you visualize this, it is easy. Red candies from one cluster, blue candies from another. The model can easily learn if the color is red, then it is predicted as spicy, and if it is blue, then it is predicted as sweet. So, given a new candy, record its color, transform its color into exposures of the red feature and the blue feature. In other words, rewrite the color in terms of our latent features. So, using the latent feature exposure of our new candy, figure out whether it is more similar to the red candy cluster or the blue candy cluster using a distance measure such as Euclidean distance. So, if our model puts it in the red color, we predict the new candy is to be spicy. Because in our original data set, all the red color clusters candies will be spicy, and if it puts it in the blue cluster, we predict that new candy is a sweeter one, since we have the original data set with blue clusters are considered as sweet. So this is how we have to do this clustering using this curse of dimensionality. So this dimensionality reduction techniques such as principal component analysis, TSNE and autoencoders were used to help us overcome this curse. By reducing unnecessary dimensions, we make AI systems faster to train, more accurate on real world data, and easier to interpret and visualize. So in short, dimensionality reduction converts complexity into clarity, so helping us turn vast data spaces into actionable intelligence. The true goal of artificial intelligence is this conversion. So this is all about the curse of dimensionality, and thanks for watching the video.